This is Boneh DeMillo Lipton. This is 1997. In 2007, there was a very humble and fun conference in Austria, where TU Graz is, called AustroChip. And in AustroChip, um, this is like, as far as I understand, AustroChip is like a conference. It's like CSCML, in Ben-Gurion. Students get there to practice their presentations, and they're trying to play with LaTeX and see how it works. And so it's not like a top tier venue, but this paper from AustroChip 2007 has a huge impact, and so it's also a very, very fun paper to read. It's called Optical and EM Fault Attacks on CRT-based RSA Concrete Results, and it's in the middle. What do we see here? What do we see here in this figure? So let's kind of zoom in, because this is a really, really fun, really fun paper. No, I didn't want to do that. I wanted the hand. So what do we see here? A laser beam. You think that master students get access to laser beams? What is this? So let's start from the bottom. So this is a bunch of aluminum foil, or I think it's copper foil. This is a programmable microcontroller, which is running RSA. This is, you know that when you do a barbecue, when you do when you do barbecue, you need to light the coals, right? And you don't want to reach in with a matchstick, because it will burn your hand. So there are these lighters, the gas lighters, the butane lighters. They're like a gun which with a little flame on the end. Fire starters, I think they're called. Gas lighters. No, it's not a blower. It's a little. You press a button, and that comes with a tiny little flame. You must have seen one of these. I'll show you one. You know what? Fine. This one. Yeah. Oh, it's in AliExpress also. Where can I find something? Just do this in Google Images. Okay? Yeah. Gas lighter. What is this? You're doing Wikipedia. Yeah, right. There is a spark. So this is a gas. So when you want to use it to fire to make a barbecue, there's a source of butane, like a cigarette lighter, and you press a button and the butane comes out and the spark lights it. And then you can just point it at the fire. So this master student took one of these gas lighters, and they removed the butane source, so it didn't throw out fires, and they added some kind of automatic control to it. And what you see here is the end of this fire starter. This is called the spark gap. Here, what happens? There's a large voltage differential between these two things, and there's a spark. The spark is supposed to light up the butane, the gas which is coming out of the lighter, but instead it's just creating a spark. Now this spark actually causes a very crazy and hard to control electromagnetic pulse. So serious science is going on here. So they put this electromagnetic pulse very, very close to the device, and this device was doing RSA CRT. And I'm going to show you a figure. This paper it's really fun because how did they do? They did the optical attack using these fun optical fibers that you put on your head in Yomat's mode. You know these things? These optical fibers with. I hope you understand what I'm doing. I'm just not making deer impressions. These light ones, these sticks with light. So they took one of these optical fibers and used it for optical injection. It's a really fun paper. So let me show you how it works, how it looks like. So the method was, first of all, electromagnetic pulse, and the fault was transient, although I can comment about that, because you read the paper to see that sometimes you're buying, yeah, exactly, it can get synchronized. They did the pulse was transient, but sometimes they broke they report that sometimes they zapped it so hard that it stopped working for an hour, and then it started working again. And they really don't know what they hit with the fault detector, but they think that they hit instruction processing. That's what they think. So let's look at this figure from the graph, and we'll try to show you what's going on here. So the x-axis is the time, and the y-axis is the power consumption. They connected the power measurement probe to the device. And they see here that, first of all, the device is doing exponentiation modulo Q. Actually, it's signing modulo Q, signing modulo P, and then it's doing the CRT combination step to combine the two. And what you see here, this peak is happening because this EM pulse is absorbed by the circuit, and now the circuit has to get rid of this EM pulse, and it actually goes to the ground. So this pulse here means that this was the moment the device was zapped. And you can see that indeed the device was zapped in the middle of the signing modulo Q. And they were actually able to get CRT based, they were able to break RSA this way. And there are some researches, there's like some evaluation in the paper. What is the distance between the probe and the chip and so on. Very fun paper. You can read it and you can be inspired. So this is Boneh, DeMillo, Lipton in practice. So two things I want to talk about before the break. The first thing is I just want to put it as a bookmark. You can see that Boneh, DeMillo, Lipton doesn't really need a really very strictly defined and like microsecond resolution and highly deterministic fault detector. So any kind of crazy stuff that can happen to the device under test can work for CRT. And this means that, and I can tell you from my experience, that if you get an inaccurate fault attack, and you can think of all sorts of ways of doing fault attacks, lasers and not lasers. If you have RSA CRT, you can attack it. And specifically, if you have an embedded device, and this embedded device is in the hands of the attacker, let's say the attacker is in control of the battery, the attacker can do all sorts of irradiation, you are really expected to do defenses against Boneh, DeMillo, Lipton because it's sensible that it will happen. And if you look at open source libraries, which implement RSA CRT for embedded devices, for IoT devices, for low-cost microcontrollers, you will see that they have defenses against Boneh, DeMillo, Lipton. Even though your system architect will say, fault attack, out of scope, it is in scope. If you look at serious crypto libraries, you will see that they put protections against this. And now my question for you is, how do you protect against this? How do you defend yourself from this attack? How do you protect yourself? What is the what can you do? So OL is saying add a random number each time. But this is a decryption oracle. What I need to answer the right. I need to answer the right answer. OL. I don't really have. So Gil is saying verifying that m sub p is equal to m prime sub p, but the device doesn't know if it was running correctly or not. The device just got, I'm inside the device. I finished calculating. I have m. What do I do? I don't know if it's the right m or not. So what can the device do? So Gil, I cannot calculate this because if I knew what the right M was, I would just output it. The device gets M sub P and M sub Q and then combines them. So how do I do this? How do I protect myself? So just, whatever you have there, add another layer. Okay, so Stav is suggesting some kind of electrical defense. So what, just like coat it in something? So you can do all sorts of, if you look at, for example, the Google Titan chip, which is used to protect their smartphones, it has a fault attack detector. If it sees that suddenly there's a huge pulse of energy, it says, you know what, I'm going to reset. I'm not going to answer. But this is kind of cheating. Because again, you can find the fault attack which is detected. How do you defend against RSA CRT attacks? The simple and trivial thing to do is you just take the result and you encrypt it. You calculate m to the power of e. And you check if m to the power of e is equal to c. Okay, so after you finish this, you just, as you're the device, you're going to calculate if m to the power of e is equal to c, right? I know what m is. I know what c is because I got it as an input. And I know what m is because I just got it as a decryption. So if m to the power of e is equal to c, it means that I was able to do my decryption successfully. And if it's not, there was a fault attack I need to fail. And you'll see if you look at open source libraries and you look at the way they do RSA decryption, after they decrypt, the first thing they do is they encrypt again and check that the encryption was right. And now my question to you is, so first of all, do you understand why this works as a defense? Why does this work as a defense? So this works as a defense simply because if m prime, if there was a fault in m sum in the calculation of m sub p or m sub q, then if I raise this thing to the power of the encryption key, I won't get a ciphertext. I'll get something else because by the Chinese remainder theorem, there is only one solution which gives me m. So I obviously got some different message. And if I raise it to the power of e, I don't get c. So this will protect against my attack. But my question for you, and let's see if you can answer this. This is another modular exponentiation. It's the most expensive operation that you can do. Won't this make my system twice as slow? What can you answer to that? There is an answer. What is the answer? I'll give you a hint. Of course, I'm going to use CRT to encrypt. But why isn't this as slow as decryption? I'll give you another hint. It's somewhere in the chat. If you look in the chat, it's in the chat. Okay, so the answer is that the way RSA is usually deployed, encryptions are much cheaper than decryptions because E, the encryption key, the encryption modulus, is chosen with a very, very low Hamming weight, a very, very small word length. So in fact, m to the power of e is much cheaper to calculate than c to the power of d. So again, if you look in open source libraries, you will see this defense in systems which are afraid of fault attacks. What do we say to the system engineer about this? We're saying, baby, you should also put this in your library. Even if you think you're on the cloud, I don't know where, you are going to get a fault attack. How are you going to get a fault attack? After the break. Okay, so let's do a 10-minute break, and let's return at 7:08, and then I'll see what I can tell you about modern fault attacks, all sorts of cool fault attacks from the past few years.